Griffiths in section 2.2.2, the induced surface charge. In the last video, there was the problem where we had an infinite conducting plane on the xy plane. We wanted to know, and there's a charge of plus q a distance d away, and we wanted to know what the potential was everywhere in space above that plane. We used the uniqueness theorem and satisfied the boundary conditions for this problem, and said that this was equivalent to a scenario where we had a charge plus q, a distance d above the xy plane, and a charge minus q, a distance d below the xy plane. And the potential was just the sum of those two values, the potentials from each of the individuals, which is 1 over 4 pi epsilon naught q over x squared plus y squared plus z minus d squared minus q over x squared plus y squared plus z plus d squared. Okay. Now, this charge doesn't actually exist. Right? This negative charge, this image charge doesn't really exist. But the charges are distributing themselves along the conducting plane in a way that it makes it look as if there was a charge minus q, a distance d below the xy plane. Okay, so let's go ahead and figure out what that charge distribution is. It's a surface, so it'll be a surface charge distribution. It's also a conductor, so charges have to live at the surface. What is that surface charge distribution at the conductor? Okay, so we have to remember that that the electric field undergoes a discontinuity across a surface with a surface charge. Right? That electric field is related to the gradient of our potential, and we can write this expression that the surface charge density is equal to minus epsilon naught, the derivative of our potential with respect to n, where n is the normal direction from the surface, or this is like the gradient essentially. Since we're doing this in the direction normal to our surface is the z-axis, we can go ahead and take this derivative of our potential with respect to z, right? And then the surface charge density exists at the surface, which is at z equals to 0. So we got to evaluate this derivative with respect to z. We then set z equal to 0, and we can get our surface charge density. Okay, so here is this minus epsilon naught times the derivative of the thing above. It's 1 over 4 pi epsilon naught. All right, I'm not going to do all of the math steps, but this becomes minus q z minus d over x squared plus y squared plus z minus d squared, all of that to the 3/2. We get a plus q z plus d over something that looks very similar, x squared plus y squared plus z plus d squared, all to the 3/2. Okay, so that was that derivative with respect to z. Okay, the next thing to do is to set z equal to 0. Right, set z equal to 0, you see that these terms in parentheses are going to be a little different. You're going to get sigma is equal to 1 over 2 pi. I'm going to add this and this will look exactly the same. The denominator will be the same, so I can have one fraction instead of two. It's going to be x squared plus y squared plus d squared to the 3/2 and minus qd. There's two of them, and the 2 canceled the 4 at the bottom. All right, so we found the surface charge density. It is a function of x and y, as you might expect. And we have this something x squared plus y squared in the bottom, which makes it seem like it's probably going to be radially distributed, something like a circle. So that sounds about right. Okay, so we have a density. How much total charge is being accumulated to make this image charge? Let's do that. I can go ahead and rewrite that surface charge density as minus qd. Instead of x squared plus y squared, we have that's like a radius squared. Okay, so that's 2 pi r squared plus d squared to the 3/2. It's the same exact expression, except I said that r squared is equal to x squared plus z plus y squared, where this distance is r, wherever we're evaluating the surface charge density. Okay, and I can find the total charge by integrating that surface charge density over an area. All right, my integral is going to be over some circular region that's supposed to be in the xy plane. So I'm going to integrate in polar coordinates. So that's r dr d phi. Okay, I have a minus qd over 2 pi integral of r dr d phi r squared plus d squared to the 3/2 integral from 0 to 2 pi. And then we have to integrate over the whole conductor, which is an infinite conductor, so the radius will go from 0 to infinity. Okay, the 2 pi comes out pretty easily because there's no phi dependence. So I get a minus qd that cancels the 2 pi on the bottom, and I'm left with the integral of dr r squared plus d squared to 3/2. Okay, you can do that probably with a u substitution. You can look it up. It becomes minus qd over square root of r squared plus d squared 0 to infinity, which becomes minus q. So the total charge induced on that surface is minus q. All right, we started with a positive test charge above our plane, and maybe it's not surprising that the way that you get an image charge to have a minus q is to distribute, smear out some charge distribution with total charge minus q along that surface.